So we have seen how to exploit buffer overflows. Now I will try to tell you how to prevent those guys and how to find buffer overflows and related security problems in your source code, or if you are too lazy to find them, how to apply dynamic countermeasures so at least the exploitation wouldn't be so easy. We're already pretty tight with time, and so I hope I will get through my slides. If not, we have to cut the dynamic countermeasures a little bit short. Then you should come to me after the talk and I will give you a private lecture. About me, my name is Martin Jons. I work at the University of Hamburg as a security researcher in the project Secologic. Secologic is a project carried through by SAP, the Commerzbank, a company called Eurosec, and us, University of Hamburg. And we try to, in this project, we try to establish what is the state of art in software security and how can we widen the boundaries so that our software gets more and more secure every time. If you're bored at work or if you're really interested in the topic, go to www.secologic.org. We have quite a couple of nice white papers on C security, PHP security, and Java, and everything, pretty much. Okay, what I'm going to talk about, I will show you tools that are applicable by the programmers. So I'm not interested in stuff that the person can do that is installing the program or that is administering the server. I only want to look at, when I am the programmer, how can I be sure that my code is not as exploitable as it used to be. Most of the tools I'm going to show you have their origins in academia. This is one simple reason. Those tools are published and we can look into the way they function, and it's more interesting to talk about something we understand than something we don't understand. These are the commercial tools. There's quite a limited market space for commercial tools to do static analysis for security reasons. But I don't know how those tools work, and I can't tell you anything about them, what you can't get from the website. So we just look what is possible in academia today. Pretty much everything I tell you today is aimed at the C language. The main reason is that the most papers that have been published are concentrating on the C language. There are a couple of reasons for this. The main reason probably is that the most severe security problems today are still rooted in the C language. C gives the program so much access to the underlying computer memory structure that an unsecure C program allows a lot of exploitation. If you go to Bugtrack and look for buffer overflow, heap overflow, or format string, you're going to find something pretty much every week. Also, C is pretty easy to check. I think this is one of the reasons why a lot of tools look at C but not C++. The control flow of a program, so the stuff that is happening when the program is executed, is mostly determined on compile time. You have something like function pointers, but they are not as heavily used as in, for example, object-oriented programming. And C programs are often vulnerable at a quite easy, unsophisticated level, at a syntactic level. So a lot of problems are caused by library functions like string copy. And so if you look at all the string copies, you may have a good idea where at least a couple of your security problems may lie. C is also quite hard to check. C depends really heavily on pointer arithmetic, typecasting. So seeing what data you have and where the data is going during your control flow is really hard with C. Also, C programs, especially bigger projects, do heavy use of the preprocessor. So I've seen projects, they seem to program more with the preprocessor than with the actual language. So this might be a problem for static too. And we also have more than one C. We have ANSI C and KNR C and blah blah C. And so if you do really sophisticated analysis, you sometimes are not really sure which semantics are behind those statements you're looking at. The tools we're going to see are not only concentrating on buffer overflows, but we also have tools that look for exploiting of heap corruption or format string exploits. Just a warning, you pretty much all know now about buffer overflows. I hope you believe me there's something like heap corruption, format string exploits, and that the tools look for this. I won't go into detail why they are vulnerable or how to exploit them. Just believe me, they exist. To make it a little bit more accessible, I have done a classification. The main classification is between static and dynamic tools, as I already told you. Static tools do the check before or during the compilation. Dynamic tools work on runtime. They compile some code in the executable that is supposed to find or prevent exploitation. This is what we're going to cover in the next hour. At first, we start looking at syntax-oriented tools. Those tools work because C is C is often, as I told you, exploitable or vulnerable on a syntactic level. So if you look at all the unsafe library functions that don't respect buffer boundaries like string copy and everything else, we're going to find a lot of problems already. So this is static tools that work on the syntactic level pretty much only do that. They look in the source code, are there string copies, are there gets operations, are there printfs with a dynamic format string, and they're going to warn you about this. So these syntactic tools pretty much work only on a per statement basis. They don't take any context in account. They look just line for line in the code. Oh yeah, there's a string copy. We may have a problem here. They don't really work on the source code per se, but they do some pre-processing. They generate a token stream, an abstract syntax tree or stuff like that. But this is as sophisticated as it gets. I've got here 3 examples for you, floor finder, ATS4, and REDS. If you're interested in this kind of analysis, all 3 tools are free, so you can go to their websites and look at them. And they're kind of useful if you have a really small project or if you're just starting your programming day. And if you're not really familiar with which library functions may cause security problems, they give you pointer to problems in your code. But they're not really interesting. Limitations of syntactic analysis, I think I've told you a little bit about already. They take only limited context into account. So they may look at type qualifiers. A string copy with a constant source may still cause a buffer overflow, but this buffer overflow is pretty surely not exploitable, so we don't need to look at this in a security context. And some tools on the syntactic level do some other preliminary checks, but they're not really sophisticated. They totally ignore complex context like inter-procedural dependencies. They don't calculate the control flow or the data flow of our program. So the consequences is pretty obvious. We get a lot of false positives if we use these programs. For example, Floor Finder reports pretty much every single string copy in our code. Doesn't really matter if it's exploitable or not. A false positive is an alert from our program that says, hey, here's a security problem, but actually there's none. So even if our program is totally secure, Floor Finder might warn us about 500 times. Other syntactic analysis or other problems that may lie on a higher semantic level. So stuff that is caused because of a sequence of instructions. For example, a double free problem. Syntactic tools are not able to find those problems. The next type of tool is on the next. I have 2 examples for this. Are the compiler-related tools. If we look at compilers, especially at modern compilers, we can do a general observation. Static analysis tools and compilers share quite a lot of common techniques. A compiler does parse the source code into an abstract representation, token stream, abstract syntax tree, or something more complicated. Even our syntactic tools do this. For optimization reasons, they generate control and data flow graphs. This is something we could use for static analysis for security reasons as well. And they do enforcement and check of constraints. For example, even a CSOM compiler does some type checks, so we are not able without typecasting to assign integer value to a character variable. So the more advanced our compiler is, the more the compiler does understand the program and does understand the semantics of the program. And if we want to do some sophisticated analysis for security problems, we should understand or should try to understand our program. So looking at compilers can help us. The first real tool that I'm going to show you is called Boon. This is short for Buffer Overrun Detection. It's from the year 2000. Boon introduces for its for its analysis a theoretical abstract data type called C-string. As you probably all know, C doesn't have a data type string per se, but it only has character buffers and a couple of library functions that work on this on these character buffers. And so this is the only things that Boon looks at. It looks at the way these library functions work on the character buffers and if they may cause security problems with buffer overflows. Boon ignores control flow, but is still able to do some interesting observations. It's done via integer range analysis. So for every C-string, as we have in our program, Boon creates two variables, one alloc s and len s. Alloc s represents the integer or the range of memory that is or that may be allocated in the memory for this C-string. Len s represents the min and the maximum amount of memory that is actually used, so how much bytes are actually written into this buffer. The safety property is pretty obvious. If for one of our C-strings the maximum value of len is bigger or equal to the minimum value of alloc, we might have a problem in It might be a situation where we write more into the buffer than we have allocated space, and so we have a buffer overflow. The analysis itself is done via integer range algebra. So we have one operation that we're going to look at. This is the operation contains. Actually, contains works on the second argument. If you have two integer ranges A and B is supposed to contain A, the analysis looks at B and tries to widen the boundaries of B if A exceeds those boundaries. For example, we have an integer range A from 2 to 5, and we have a constraint that says A should contain at least the range from 4 to 7. After this operation, A will equal the integer range from 2 to 7. So for every statement in our program code that work on the C-strings, the program or Boon constructs an integer range constraint. For example, if we have a C-string S and we allocate 6 bytes of memory for this, we have the constraint that the integer range alloc of S should at least contain the integer range 6 to 6. If we read into this buffer with fgets, fgets reads from 0 to a maximum number of bytes, in this case n. We know that the length of S should contain at least the range between 0 and n. Okay, not so fast. And string copy, really important one. If we copy from source to destination, our range that is constrained, or the constraint is constructed, is that the length of the destination should at least contain the length of the source. How this is computed, I'm going to show you a little bit more in detail. After the program has constructed all those constraints, a direct graph is built. The vertices of this graph are our variables, and the edges are the constraints. And remember, the constraints represent functions or function statements of our program that work on those buffers. So this is a really, really small program that we try to construct the graph for. We have 4 vertices. This is our 4 variables: length for source, alloc for source, length for the destination, and alloc for the destination. The first statement in our program constructs 2 constraints, 2 interrange constraints. So the length of our source string should contain at least 13 to 13, and the allocation of our source string also should contain at least the range between 13 and 13. The second statement gives us the next 2 constraints. It's pretty obvious now. Alloc of destination should contain the distance between 8 and 8, because we allocate with malloc exactly 8 bytes of memory. The length of destination right now is still in the range between 0 and 0, because we haven't dereferenced destination at all. The last line gives us only one constraint, that the length of destination should contain at least the length of the source. So, After we build the graph, a constraint solving algorithm works on the graph. It descends through the graph until all variables are stopping. So it descends through the graph, and every time it encounters an integer range constraint that causes one of the variables to change, it changes the variable accordingly. We can't be sure that after one descent through the graph, all the variables have their finite state. So we have to descend through the graph until a so-called fixed point is found. A fixed point is when we are finished with the descent through the graph and all the variables stop changing. This is a technique that is heavily used in compiler optimization, for example, for finding dead code or to calculate liveness of variables. Therefore, this approach is quite related to compiler optimization. A potential buffer overrun is found if we have some variable where ln, or the length von s, is bigger than log of s, and we have something like here. If you see, the length of the destination is in the range between 0 and 13, but the allocation of destination is in the range between 8 and 8. So the minimum allocation for destination is smaller than the maximum length of destination. We have a buffer overflow here. Okay, next tool we're going to look at is called cqual. Cqual is short for something like C with type qualifiers, and this is what cqual does. cqual is inspired by Perl's tainted mode, so the web hackers here in the room should know what this is. Tainted means something like don't trust this value, so a tainted value is not trusted. cqual is used in this example at least to detecting format string vulnerabilities. Format string that could be influenced by user input is quite exploitable, therefore we want to try to find this. How to do cqual does the analysis the way it does an extension on the language type system. It introduces two new type qualifiers, tainted and untainted. So we have two new type qualifiers, tainted and untainted. And type qualifier is in C something like we have the type of the variable, and sometimes we have also qualifying information, like this variable is static, this variable is const. So const and static, the keywords are also type qualifiers. cqual introduces more type qualifiers, even this tainted and untainted. Tainted means this data should not be trusted. Untainted means this data is safe, do whatever you want with it, you are on the right side. So if we don't know, so we are able to write in our source code, okay, this should be tainted and should be untainted, but we have got a lot of variables, and sometimes we don't even know if this variable is tainted or untainted. So for every variable that is not where we don't know if it's tainted or untainted, we do type inference rules to apply or to propagate this type qualifiers. In the example we have an integer a, so it's a variable a. We don't know if this is tainted or not tainted, but we have a tainted variable b. If a gets assigned a value that is directly derived or is directly dependent from a tainted value, a inherits this type qualifier, so a is not trusted anymore as well. So cqual used this oh, this is not really interesting. This is some theoretical background, but all we want to know is that it is forbidden to assign a tainted value to an untainted variable, and it is allowed to assign untainted values to a tainted variable. So we only want to make sure that our secure code or our vulnerable functions don't get untrusted data. And this was two examples. At first, we have got a function f. F allows untainted parameters, and we have an untainted variable int r. So if we call f with a, there's no problem. This is okay. In the second example, we got a function g. G does some vulnerable stuff, so we don't want tainted data as parameter into a g. So we say, okay, g only takes untainted stuff. If we've got a tainted variable b and we try to call g with b, we got a type error. Okay, cqual finds format strings the following way. The goal is to find all data paths that lead from user-controlled data to the definition of a format string. So all functions that may contain user data, like reading from the command line or reading from the network, the return values are marked as tainted. And all parameters that have a format string, this format string parameter is marked as untainted. So we have our, in this case, getEnv. getEnv reads from the environment that is user, that can be controlled by the user, and reads a character buffer from this. So we declare this as tainted. And we have printf, and printf, the first parameter of printf is the format string, so we want only untainted data here. We have a character array s. We don't know what s is, but if s gets assigned a value that is derived from getEnv, then s gets marked tainted. If you try to print s or doing printf with s a format string, we have a type error and a problem here. Okay. Next class are the theory-based approaches. Theory-based approaches share in common that they look at the discipline of theoretical computer science. So the students here should know a little bit about theoretical computer science. We look at two things or two disciplines that are done here: the finite automatons and the program verification. Okay. XGCC is one of my favorite tools. Unfortunately, it's not freely available anymore, but the internals are still, the papers are still there. XGC has been, from XGC there has been built a commercial tool called Cavity, but XGC is quite interesting what it does. XGC uses finite automatons to track the assurance of some conditions. So we're going to see how this is working. The automatons can be described in a program language that is owned for XGCC. The program language is called Metal. The check is done as follows. XGCC creates a control flow graph from source code and walks this control flow graph after its construction. If there are statements, so every automaton we create with Metal has a creation rule and has some transitions. And a creation rule is pretty much a pattern matching. If we find something in our source code that triggers the creation of this automaton, the automaton gets created, obviously. The transitions are also something like pattern matching. So if you encounter with an automaton that is already created and we encounter a statement that is triggering one of the transitions, the state of the automaton gets updated. I have an example right following. Something interesting also is if we encounter a branch, so some condition, if statement, a switch statement, stuff like that, and we have an automaton that is affected by this branch for some reason, then this automaton is duplicated. We have then two automatons, one for the true tree and one for the false tree. This is done to reduce false positives. So this is one of our automatons, and this is a really nice PowerPoint slide. I don't know how to work this program, but I hope it's kind of obvious. We have got an creation trigger. This is whenever a pointer v is declared in our C code, a new automaton is created. The automaton is in the initial state v initialized. That means, okay, we have a pointer and it's initialized, but we don't know anything else about this. This automaton is used to find double free errors. Double free errors are one of the ways to exploit heap corruption. I don't gonna explain how it does, but believe me, if you do two frees on the same pointer, you might have security problems there. So if in this source code, if in control flow graph, we encounter a free operation on this pointer, our automaton gets a new state. It's a state v freed. This state is the last legal state for the automaton. We have two more transitions, another free and differentiation, but those lead our automaton to error states, to the double free state or illegal access state. Okay, the example, we have a short piece of code. In the first line, pointer is declared, therefore a new automaton is generated, and it starts with the state initialized. The next two instructions work on the pointer, but don't trigger any of our transitions. Then we encounter free of v. So v is freed, or actually the automaton v is set to the state freed. Now we have a condition. We have a true branch and the false branch, and we see in both branches v gets there are operations on v that trigger transitions. Therefore, we have to duplicate our automaton. We have now v1 and v2. Both of these automatons inherit their state from the original. In the first branch, we try to dereference v. we get an error state illegal access. In the false branch, we got our second automaton also gets an error state, and this time because of the double free. Okay, there are. I had to throw out at least half of the tools I wanted to show you because of time constraints. There are more than one example for every of these categories, but I only show you one. So, and now we're going to look at program verification. Program verification is a rather old technique that with the aim to prove that the program code we write is actually doing what we want him to do. It works with pre and post conditions. So for our program P, we define a precondition, a post condition, and we want our program to ensure the post condition if we ensure ourselves that the precondition is met. So for hello world, our precondition would be nothing. Our post condition would be on the program puts out hello world. If we have sophisticated problems, this is rather hard to prove. To make it short, our program is translated in a couple of single statements. The single statements are assigned pre and post conditions with the so the pre and post conditions are that the post condition of S1 is equals the precondition of S2. Those conditions are specified in first order logic, and if we can prove the correctness of all those small conditions, then we have proven that our program actually is doing what we want. This is really complicated. It works quite okay if you do it on really small programs like device drivers. There's a lot of research going on there. But if you try to do this for Apache, you might be out of luck. Security tools that use this or that borrow from this approach only define pre and post conditions for special constructs. So in our case, we're going to see it only looks or only defines pre and post conditions for library functions that work on buffer arrays like string copy, and also on other statements that do stuff on on character arrays. We look only here at Splint. Splint is a really sophisticated and mature tool that is used for all kinds of debugging applications, but it can be used for finding security problems as well. It uses pre and post conditions for detecting buffer overflows, and how it does this with the introduction of four constraints. And they are quite similar to the ones we have seen with Boon. So we have a max set and min set for every buffer, and we have a max read and min read for every buffer. So max set and min set is the amount of memory that is allocated for this buffer. Max read and min read is the stuff that we write in this buffer. So a precondition for our string copy would obviously be that the max set, so the maximum amount of the destination string is bigger than the maximum read of the source string. Splint is also quite smart. Splint is able to, for some of the more basic statements of the C language, Splint is able to detect both conditions and preconditions as well on its own. So if we define a character buffer with the size of 42, Splint knows that this statement ensures that the minimum set of the buffer is 0 and the maximum set of buffer is 41. The analysis pretty much is done that we construct a control flow graph from the source code. We walk through the control flow graph and calculate all the pre and post conditions. And if we meet a point in the control flow graph where we can't, where the program is not able to make sure that the precondition is met, then we get a warning. Okay. Oh, I'm pretty quick. I'm sorry. So I maybe threw out too many tools, but then you have more time to drink for drinking coffee. The dynamic approaches. The dynamic approaches work on runtime. They alter the way the program is compiled. They do this, there are two ways to do this. They might actually alter the C code that gets compiled, so you have a pre-processing that might do some additional, put some additional C code into your program, or the compilation process itself might get altered. After this, we have got an executable that is smart enough to find security problems on its own, or at least we hope so. The next tools I'm going to show you only present tools that check for buffer or for stack-based buffer overflows. There are dynamic approaches for format string exploit and heap corruption as well. I think if you know, I think he talks the day after tomorrow, will at least tell you a little bit about dynamic approaches for heap corruption. So go and watch his talk as well if you like this topic. If we compare dynamic versus static approaches, we see where the advantages of the dynamic approaches lie. If we have a sophisticated static tool, then this static tool tries to determine runtime conditions before we actually do the compilation or the execution. So a sophisticated static program tries to estimate how the control flow of the program might be and does some loop heuristics, how often does this loop execute, and also do some data flow estimations, where starts my data in the program and where does it end. Dynamic tools doesn't need to do stuff like that. They know what the program is doing because they are the program, and they know where the data is flowing because they are processing the data. We have two classes here. We have the detection class and the prevention class. The detection class is somewhere in the middle between the static and the dynamic analysis. We've got one example here. It's called Stobo. This is for systematic testing of buffer overflows. And the name gives it already away. Stobo doesn't produce any production code. Stobo puts out an executable that is should be used solely for testing the program. The developer of Stobo say that they are a dynamic extension of Boone's approach, so we might have some familiarities there. Stobo does track the possible buffer lengths during execution, and actually I think I've done the wrong word in italics, because what Stobo does and what other dynamic approaches don't do is Stobo looks at the possible buffer lengths, not at the actual buffer lengths. We're going to see what this or what is meant by that. The tool is supposed to accompany program testing, I already told you. So how does it work? The source code of our program gets altered before we compile it. So for every statement in our program that works on our buffers, we alter the source code. So all functions that could lead to buffer overflows, like string copy, get wrapper functions that only do the string copy but also do some checks. And if one of the wrapped functions detect a potential buffer overflow, we get a warning. Example here, we got our source code. So the declaration of a character buffer of the size 100 looks after Stobo worked on the source code like that. We still we still declare the buffer, but then we call a function called Stobo stack buff, where in the global table of so Stobo has a global table of all the buffers and all the buffer sizes, and this function just does memorize that buffer and the size of buff is available right now. If we do heap allocation, it looks like that. We also, Stobo also just declares a pointer, but the malloc is wrapped. So we don't call malloc directly, but we call Stobo const mem malloc. Stobo allocates the memory, but also does an entry in the global table that we have now a buffer called pointer with the size of 20. So if you do a string copy from buffer to pointer, Stobo uses its own, translates this to its own function, Stobo string copy. And Stobo string copy, before Stobo is executing the string copy, Stobo looks at the size of buffer. Stobo knows the buffer has a size 100, and Stobo looks at the size of pointer, and Stobo he sees, oh, we only have allocated 20 bytes for pointer. So we might have a problem here that in some time, even not with the actual data I'm working right now during the execution, but if somebody that is using the program is trying to overflow me, he might write too much memory or too much data in buffer and overflow pointer. So Stobo is able to notice that we might have here possible buffer overflow. again, Stovall looks at the potential sizes. Stovall doesn't know or doesn't care if right now, during the execution, buff may only contain the word foo. But it knows there might be a situation later in the program execution, or if somebody else tries to execute a program, where buffer actually contains all 100 bytes, and therefore Stovall finds buffer overflows that stuff like stackguard not find by every time. And this is a good introduction to our next class, those dynamic tools that prevent the exploitation of buffer overflows. And they are the class of stack protectors, and at least this is the class I'm going to show you. There are some other approaches you should. I'm going to put a director's cut of my slides with all the missing tools up on the Congress website, and also with more information if you like to read a little about this. Stack protectors try to prevent the exploitation of buffer overflows by altering the underlying program semantics. So they some of them enhance the function prologue and epilogue. Some others might have something like a separate stack for the return addresses, and some others do reordering of local variables. The most common way for stack protectors are the ones that use canaries. Canaries or a canary value is something that is written on the stack that is supposed to protect our return address. So the dynamic tool is altering the compilation process. We've seen in the presentation right before me how the function prologue and epilogue looks like. The prologue does some stuff on the stack, and the epilogue does some pops. Those stack protectors add some code to the function prologue and epilogue to check if the canary is still valid. Just look at the example, then this should be easy to understand. We have a stack frame here with the function parameters, the return address, and then we have a canary value right in front of the return address. And then we have the saved frame pointer and our vulnerable buffer. If somebody tries to copy a shellcode into our buffer and do a buffer overflow, the shellcode is written to the buffer, written over the buffer boundaries, and is overwriting the canary value. When we return from this function, the function epilogue looks if the canary is still valid. If the canary is not the value we expect it to be, in this case it's LLCO, then an alert is produced and usually the program terminates. Yeah, canary gets overwritten, the attack detected. There are a couple of different types of canaries that you can write on the stack. There's a random canary. This is just a random value, so that that attacker can't guess what canary might be used and use this in the shellcode at the right place. There's something like a random XOR canary. I don't think it's used in the wild anymore. Something like that we have a random canary that is XORed with our return address, so we have a different canary for every function. There's a null canary, and more interesting, the terminator canary, which is a special case of the null canary. The terminator canary contains all characters that cause unsafe library functions to stop writing to the buffers. So there's the null byte, the first thing, stops a string copy with this operation. I think the next one, the new line, is supposed to stop gets and fgets and so on. So the terminator canary is obviously that you can't construct a shellcode that contains the canary, or if you try to contain the canary into your shellcode, the overflow operation will be stopped. Yes, stack canaries only protect against buffer overflows that are trying to overwrite the return address. We have no protection against heap overflows for mastering exploits. Also, no real protection against pointer overwriting or the alteration of local variables. There are a couple of tools that use stack canaries. The most common or the most best known is stackguard. Then Microsoft tried to copy stackguard with their Visual Studio.NET compiler, but they did it really poorly and introduced new security vulnerabilities with the implementation. And GCC, I think, it now contains per default something it's called Propolis. This is in development by IBM Research. And I'm going to show you how this works. It's, okay, additional programs, when canary, this is pretty obvious. If a canary violation gets detected, our program execution stops, and therefore we just alter our vulnerability from a remote code injection to denial of service, and I don't really want that on my web server as well. Okay, Propolis. Propolis does pretty much the same as other stack protectors. They use canaries as well, but they are a little bit, Propolis a little bit smarter than the dumb stack protector I was showing you. Propolis reorders the values on the stack. So the local buffers are located, when you have a stack frame, are located between the local variables and the guard value. So if we have a local buffer and we have a buffer overflow, local variables don't get overridden anymore. So if we have a function pointer in our program and we have a buffer overflow, the buffer overflow is not able to override the function pointer anymore. Also, our saved frame pointer is protected by the guard value. There used to be exploits for simple stack guards where they just altered the frame pointer and not the return address and constructed a fake stack frame which contained then a fake return address. This attack is also prevented by Propolis. The only thing, if we look at this as stack frame layout, the only thing that is still overwritable, which could cause problems, are the function arguments. If we have function pointers in our function arguments that are dereferenced before the function returns, we may still be exploitable, but Propolis knows about that. So Propolis does protection of function arguments through local copies. If we have a function bar that expects a function pointer func as a parameter, without any protection, this function pointer can be overwritten by a buffer overflow of buff, and so func can point to anything we want func to point to. Propolis does this with our program. Propolis introduces a new local variable called local func, and the first thing it does is copying every function pointer argument of our program into this local copy. So the character buffer lies above this local func. So if we have a buffer overflow that is overflowing buff, the pointer, so the function parameter func is still overridden, but at a point of time where it doesn't has any significance anymore, because in the rest of the program, local func is used instead. So this attack doesn't work anymore. Propolis is not perfect. The Propolis is not able to reorder elements of or stuff that is hidden in structs. So if you have a struct that contains, for example, a buffer and a function pointer or stuff like that, then you're still out of luck and still exploitable. As well, it doesn't really protect the overwriting of pointer arrays. So if you have an array of function pointers, then we still are able to write into this buffer. Okay, conclusion, perfect timing. The conclusion is I don't really know where we stand. I don't know what the current limitations of static analysis for security problems are. There are no good surveys to show us which kind of vulnerabilities are really detectable right now and which kind of vulnerabilities are not covered. This is something I do in my research. I want to find out what is possible today. Also, I'm not really sure what the actual ratio is between real vulnerabilities and false positives, because the more false positives we have, the more time it takes to work with the analysis results of our tools, and the more unwilling program managers or product managers are willing to use these tools, because if our development process takes 3 times longer because of those tools, we won't use them, I think. The static tools pretty much ignore completely C++. I think maybe it's too hard, I don't know, or if they think who's smart enough to use C++ is smart enough to write secure code. It's just an observation I made. Also, all the static tools I presented you have a narrow focus. They only do bounds checking, or they only look for mart strings, or time of check, time of use. So if we want to find all our problems in our source code using these free tools, we have to use more than one tools on our code. So we have even more false positives, which kind of sucks. The commercial tools do everything in once. So they they are better in this direction. The dynamic tools have the problem they only attacked against known attack vectors. So if you find a new way to exploit, for example, format strings, or a new way to exploit heap-based buffer overflows, which just has been published on Bugtrack, then our dynamic countermeasures are helpless. Thank you.